over the past few videos, we have been discussing some of the potentials that have spherical symmetry, and in particular we took a look at the hydrogen atom, and afterwards we saw angular momentum. And one of the conclusions was that both for the hydrogen atom, and in fact any potential that has spherical symmetry, and also for angular momentum, the eigenfunctions, at least for the angular momentum, and the solutions for the spherically symmetrical potential were the spherical harmonics that depended on quantum numbers L and M. However, there was one important difference. So when we solved the Schrödinger equation for this spherically symmetric potential, we saw that L could be 0, 1, 2, 3, 4, and so on, basically any integer that is not negative, and we saw that M could go anywhere from minus L to L. But when we found the eigenfunctions for the angular momentum, we saw that L could take any value from 0, 1/2, 1, 3/2, 2, 5/2, and so on. So there are some, and M could take the same, it had the same restriction, which was from minus L to L. So there are these extra terms here that make us think what's going on. Okay, and one of the things that we will do now exactly is take a look at some of these values. And in fact, it is important to see then that some of these answers for angular momentum are not really inside of the solution. They do not commute then with this wave function, and thus we can consider them somewhat separate from the other solutions from angular momentum. So basically, this leads us to think that there exists some other form of angular momentum that doesn't depend on the coordinates, because remember, this that we saw here depends on theta, on phi, the angle at which you are in the spherical coordinate system. But there are some solutions that apparently do not depend on it. So there has to be some angular momentum that doesn't depend on the spatial coordinates. And in fact, this agrees on this. It has also been seen through a lot of experiments which needed something else to explain some phenomena that were occurring. There is, for example, the Stern-Gerlach experiment. That is a very famous one where they saw that there exists this intrinsic angular momentum. And this intrinsic angular momentum is what we call spin. And it has very, very similar characteristics to angular momentum. In fact, most of the things that we derived for angular momentum will also be valid for spin. And just a quick intuition about spin, the usual analogy that is used for spin is to imagine that you have an electron, which is, let's say it's some sort of ball, and you just imagine that it is rotating, and it is that rotation of the electron that causes this spin. However, it is important to note that this is only a good analogy for you to understand that there is something intrinsic about this, but in fact this is not the way it happens. It isn't that the electron is rotating, because there is actually, maybe we'll do the calculation in some other video, but you could see that if the spin were due to the electron's rotation, it would have to be rotating faster than the speed of light, which is obviously not something that could happen. So there is that. And another analogy that I like, or at least it's kind of just a fun phrase, is that spin is like, to describe spin, is to say it is if an electron, if you have a ball that is rotating, that's basically what spin is, except you don't have a ball and it's not rotating. So that is a way I like to think about it. Just keep in mind that it's something intrinsic, okay? This is a part of the electron or whatever, because in fact, most, every particle will have some value of spin. It might be 0, but all of them will have some value. Well, anyways, that's spin. So let's take a look at a little bit of formalism here. So we know for angular momentum, if we are L squared acting on some state, now we're going to begin using a notation that goes like this. So we're at L comma M in a ket. So this is a state, and the only things that we care about when we have a state when you're going to use these angular momentum operators are the quantum numbers L and M. So that's why we usually call them like this. And now and this, remember, is simply h bar squared L plus 1 L comma M. That much we know, and also LZ acting on LM. This is h bar M acting on LM. And then we have these L plus or minus operators that act on L comma M. And this gave us, let's see if I can remember it, h bar L plus 1. Then we got minus M plus or minus 1. I think that's what it is. Acting on L comma M plus or minus 1. Right, this changed the value of M. These are the ones that we saw. And we're going to see that there's going to be a very, very similar way to use, because remember, spin is basically angular momentum as well. All of this also applies to spin, because this is just a particular case of angular momentum. But what we usually like to do is that instead of L, we're going to use an S. And that goes actually both for capital L and for small l. So this is going to be small s, and then this right here, all of that is just going to be s. So s plus 1, s, and the same for all of this. So this is going to be sz, s plus, well, that was kind of a small s, s plus or minus, and then here we have SS, and there's another distinction that is usually made, and that is to put a small s under M, because this is the quantum number M, but this one is regarding the spin. Okay, because you can have separate values for those. We can remember, well, because especially later when we see addition of angular momentum, we're going to consider both normal angular momentum and also spin angular momentum. So let me just change all of these to S. Okay, so this, and this. So the theory of spin angular momentum is basically the same as angular momentum. However, there are some interesting things that we want to look at. And in fact, let us begin by considering, and well, before we can actually go into that, we have to decide which value of spin we want to take a look at, because spin, as we say, is intrinsic to particles. So each particle has some value of spin, and that's it. That's the value you're going to use. It's not like you can just go ahead and use some operator or something to change the particle itself, because the particle is the particle. It's not going to be something else. So usually the spin that we are going to use the most, especially in these kind of courses, is spin 1/2. Because that is the spin that is the value that most of the matter has. Obviously, there are cases with other spins, but this is the most common. That's what electrons, protons have. I think neutrons too. So, and basically most of the matter that we see every day. So that's very important. So let's begin then by using this case. And I think in a future video, I'm going to just talk a little bit about the case s equals 1, but that's just to show you how you can apply this logic to other spins. Now, if s is 1, what are the possible values for ms? Right, this can go from -s to s. So that means that this can be minus 1/2, because it has to go in integer steps. That's very important, remember. So there are two possible values. Now, this is usually what we call spin down. Maybe I shouldn't put an arrow there if I'm going to note it. And this is what we call spin down, and we many times use an arrow pointing down. And this is spin up, and it has an arrow pointing up. Now, don't think too hard about why it's up or down. This is just to show that they are opposite spins, right? There isn't much of a physical way to think about it in terms of like something you can observe, like actually see is something going up or down. So these are just opposite names. Okay, that's why they're called like this. So these are the two possible states. So any, let's say we have some state that we denote like this, then there are only two possible combinations. So we are going to have some constant, some coefficient, times one of the possibilities, which is going to be, let's say, the one with positive spin, and plus some other constant times the state that represents the one with negative spin. Okay, so a way to write this, because remember, these are the only two possibilities. Any state in which a particle with spin 1/2 is in has to be a linear combination of these two states, because there is no other possibility. So what is usually done here is that we choose some vectors for these spin states that are the basis for a complete state. And what is usually picked here is that we say, okay, the one with spin up is going to be 1, 0, and the one with spin down is going to be 0, 1. This is the smallest space that we can use with the conditions that we have with these two states. So we need 2 dimensions, and each one of those is going to be the unit vector for that state. So anything in the up space is some multiple of 1, 0. Anything in the down state is a multiple of 0, 1. And these vectors that denote the spin states are usually called spinors, right? It's kind of a mix between vectors and spin. So that's important, and that's very interesting now, because now we're going to introduce a lot of vectors and matrices into what were before only functions. And that's why it's going to be interesting to find what are the operators s squared, sz, sx, whoops, that's supposed to be an x, sx, sy, even s plus minus. We want to see what are all of those things in their matrix notation. And how can we do that? Now let's begin remembering, of course, our two spinors are 1, 0 and 0, 1. And the action of any of these operators will give us, and in fact, maybe let's begin by these 4, since s plus and minus can be a bit confusing. For example, s squared acting on some state s, ms, this will give us some quantity, which we know is h bar squared, s plus 1 acting on s, ms. But this, we know, can be rewritten as this state 1, 0. This means the same. So we would want to write this in some sort of matrix notation, because we know that if we do this, we need to get some number times 1, 0, since the state is not changed by this. So what kind of matrix, when multiplied by this 1, 0 column vector, would give us just another column vector with 2 rows? And the answer is, that's a 2 by 2 matrix. So we're looking for a 2 by 2 matrix, and that's actually going to be the shape of all of these operators. And that does come, of course, because we are dealing in 2 dimensions here, since spin 1/2 only has 2 possibilities, so there's only 2 dimensions. And of course, if we were dealing with some higher values of spin, these matrices would get larger. But for now, we're only dealing in this simple case with only 2 dimensions. So let's begin building this S square matrix, and then we will work with all of the others in the same way. So let's see. What we want to put into this matrix is basically what happens to each one of the components. So remember, our spinors are 1, 0, 0, 1. Just as a quick reminder, we could put them together like this. I like to do it. There's a more formal way to do this, but since we haven't really gotten into the mathematical part of that, and I think maybe that's something I'll save up for maybe later, or I can add a video afterwards if there's enough interest. Just remember it for now, because it can be a bit helpful when visualizing this. So first, we were acting on this up state. So let us begin by taking the bra and ket of this S square operator for the up state, which means this ms is going to be in its up value. So let's actually maybe write this right away with our actual value. So S is 1/2, MS in the up state is 1/2, comma 1/2, 1/2. And now let's do the same, but this time our ket is still going to be in the up state, but now the bra is going to be in the down state. So we're basically combining them. Make a combination of the down and up states. S squared, 1/2, 1/2. Okay, so this ket is up, this bra is down. And then we have in this next column, we're going to now do it differently. So this is still here. Take a look at this. So this part right here is what changed when we went down. So now when we go to the right, we're going to leave it B. And now we are dealing not with the up state, but with the down state. So this is going to be with a -1/2 in the ket. And this is once again a cross term. So this is bra up, ket down. And finally, in this part right here, this is going to be only down state. So 1/2 -1/2 S squared 1/2 -1/2. And that's why I mentioned briefly that we should remember what the spinors are, because this right here is up, up, and you can see it as in the 1, 0 part. This is the up, and the other spinor is 0, 1, and this is where it's only down. And these two off diagonal terms are the ones where they are mixed. So let's calculate this, because we can calculate this, okay? If this might seem confusing, but remember what happens when S squared acts on some ket. This is going to give us H bar times S plus 1. So what is S here? S is 1/2. So we're going to get is 1/2 times 1/2 plus 1 H bar squared. But this is 3/2 times 1/2, which is 3/4. And then we are going to get this 1/2, 1/2, 1/2, 1/2 inner product. But this is just 1, okay? That's basically saying 1, 0, 0, 1. And this is simply 1, because these are orthonormal states. Okay, so we are just going to get rid of it because that's 1. And now here we are also going to get 3H bar squared divided by 4, but now the inner product, what is this going to be? This is now the down state. So this is 0 and 0, 1 times, and this is the up state, 0, 1, 0. So this is 0 plus 0. So this right here is simply 0. Right, and that's because these states are orthogonal. Similarly, this right here is also 0 because it's the inner product between two orthogonal states. And if you want, you can check yourself just by applying this inner product between the two, this bra and ket. And finally, right here, now this is very important. S squared is S plus 1 times H bar squared. Please remember that the first term here, this is S, this is MS. So don't use -1/2 here, okay? So we're going to get 3H bar squared divided by 4 once again. And the inner product there is going to be 1, that's why we are not showing it. So S squared is going to be 3H bar squared divided by 4, we can just factor this out, times 1, 0, 0, 1. Okay, so this is this operator in matrix form for the particular case S equals 1/2. Okay, you could write this now in more general form. You can't really just get an easy formula because the matrix will get bigger if the spin gets bigger, so you would have to calculate this again. And we'll probably do it in a later video, maybe for spin equal 1 or something, but that's for later. Okay, so let's now go for the operator SZ, and we're going to proceed in exactly the same way. So first term is going to be 1/2 1 half, this is S, this is MS, and then SZ, and then 1 half, 1 half, right? This is up state. But what is SZ? That's simply H bar MS, acting on the same state, but we're going to have an inner product between the two states. They are orthonormalized, so that means that inner product is 1. So we're only left with this, and MS is 1 half. And down here, we're going to have 1 half, comma, minus 1 half, SZ, 1 half, 1 half. So this is once again going to be 0 orthonormal states. And similarly, this other off diagonal term will be 0. And finally, here we're going to have the 1 half minus 1 half times SZ, 1 half minus 1 half. So once again, orthonormal state, the inner product will be 1, and all that we are left with is going to be H bar MS, and this time MS is minus 1 half, because that is a down state. So this is going to be H bar divided by 2 times 1, 0, 0, minus 1. Okay, so that is the matrix form for SZ. Now, the next thing that we want to do is find the matrix form for SX and SY. However, we don't have the explicit form just yet, right? We don't have, just like we did here, some procedure for the operator. We could find it, but the easiest way to proceed is to instead find the S plus and S minus operators and then use those to find SX and SY. And why is that easier? Because S plus is SX plus I, whoops, not L, SY, and S minus is SX minus I, SY. So we can use these two equations. If we add them up, we get 2SX is equal to S plus S minus. So this means that SX is simply 1 half of this quantity. And similarly, SY, we get it by subtracting these two. So this is going to be 1 over 2I, S plus minus S minus. So if we know S plus and S minus, we can find both SX and SY very easily. So let's do that. So S plus. Now remember, S plus, when it is acting on some state S, MS, this will give us H bar square root of S plus 1 minus MS plus 1. Okay, so we have this now, and by the way, this is acting on S comma MS plus 1. Okay, so let's build the matrix in the same way. So this time it's going to be a bit different. So let's take a look at this. So first we have the state 1 half, 1 half, S plus, 1 half, 1 half. Now, what happens when we apply this operator? What we are going to get is going to be, well, this whole thing, which is H bar square root of, that's going to be 3/4 minus, and then we have 1 half, 3 halves, right? Did I do that correctly? Let me see. A ver, voy a esperar igual. ¿Está bien esa fórmula, no? Sí, está bien. So let us now apply this to the first state, to the up state. So here we're going to get 1 half, 1 half times S plus 1 half, 1 half. But when we apply this operator, we're going to get some number, which can just go outside. And then we're going to have the inner product between 1 half and not 1 half, because remember, we have to add 1 to this. So 1 half plus 1, this is 3 halves. So these two states are different. They are different values of spin. They are orthogonal here. So this right here is simply 0. Similarly, for this state down here, we are going to get 1 half, comma, minus 1 half, and then the s plus operator, which will just give us some number, times what used to be 1 half, 1 half, but now it's going to be 1 half, 3 halves. So this is also going to be 0. Orthogonal states, this is 0. Now, what is going to happen here? In this state, we have 1 half, 1 half, s plus, and 1 half minus 1 half. So now when this operator acts, what we will get is going to be some number times 1 half, and now minus 1 half plus 1 is just 1 half. So this time, this right here, this inner product will be 1. So the value of this will simply be the value of alpha. So we actually need to calculate that. And that number is simply what we get from this. So h bar, square root of s, which is 1 half, s plus 1, which is 3 halves, minus ms, but ms is minus 1 half, so it's positive. And then we have minus 1 half plus 1. So when we do that, let's see. This is 3/4. And here, this is going to be plus 1 half. So 1 half plus 1 half, that's just going to be 1/4. So 3 plus 1 divided by 3/4 plus 1/4, this is simply 1, and square root of 1 is 1. And finally, this last term is also going to be 0 because it's going to be 1 half minus 1 half, 1 half minus 1 half, and then you apply the raising operator, so you get plus 1, and now they are orthogonal. So it's going to be 0. So that is the s plus. Now similarly, we can go for the s minus state. And in that case, this formula changes slightly, so it's going to be s minus here, and this plus here changes to a minus. And well, very important, let's not forget, this plus here also changes to a minus. So now the s minus equation, let's see. So this first part is going to be 1 half, 1 half, s minus 1 half, 1 half. Now you can see that this is also going to be 0 because when we apply the lowering operator, this part right here, this m will go to m minus 1. So this will be minus 1 half, and we will have orthogonal states. So this part is just going to be 0. What do we have here? 1 half. This is minus 1 half. Then we have s minus acting on 1 half, 1 half. Now this time when we let this operator act, it's going to give us some number, and this is going to be reduced by 1. And this time the inner product will be 1 because it's the same state, just the inner product between the brand ket of the same state. The state is normalized, so it's just 1. So what is this alpha? We calculate it from here. So h bar, what is s? S is 1 half, so this is going to be 3/4 minus, and m in this case is 1 half, so we get minus 1 half, and then we have 1 half minus 1, so this is going to be just minus 1 half. So here we get minus minus, this is going to be plus 1/4, so inside the square root we are going to get simply 1, so square root of 1 is 1. So, and let me write it like this, h bar. Okay, so this state over here is going to be 1 half, 1 half, and then s minus, and then 1 half minus 1 half. So when we apply the lowering operator, this minus 1 half will be minus 3 halves, So you can see that this is also going to be 0. And finally, this one right here, it's going to be 1/2 minus 1/2 s minus 1/2 minus 1/2. And when you apply the operator, this will go to minus 3/2, and it's going to be orthogonal once again. So this is also 0. And now, by the way, we can rewrite both of these matrices as just h bar times 0, 1, 0, 0, and this one h bar 0, 0, 1, 0. Okay, so we know s plus and s minus. Let me maybe rewrite this so that we can see all of this at the same time. Okay, and let's now remember the formulas that we just found. So Sx and Sy in terms of these other two operators. So this is what we found. So what is Sx? Sx, maybe I'll change colors here. Sx is simply S plus, so that's going to be 0, 0, h bar 0, plus S minus, so 0, h bar 0, 0, and all of this times 1/2. So this is simply going to be h bar divided by 2. We can factor it out. 0, 1, 1, 0. This is going to be Sx. You can see that it's actually quite quick and simple to find it like this. And Sy, this is 1 over 2i h bar, which is going to come from these other matrices. So S plus minus S minus. So S plus is 0, 1, 0, 0. I already factor out the h bar, minus 0, 0, 1, 0. So this is going to be h bar divided by 2i, and then we have 0, 1, minus 1, 0. And well, we could in fact rewrite this multiplying and dividing by I, so that we get minus I h bar divided by 2. And instead of writing it like this, we can actually put the minus and the I into our matrix. So we get h bar divided by 2, and we get 0 minus I 0. Okay, so now let me grab these and put them right here. So we got Sx, Sy, and we already found Sz here. So this is Sz. So these are the operators that give us this spin angular momentum value of our state. Now notice all of them are multiplied by h bar divided by 2. So something that is done very often is that we say, okay, let us create some sort of vector that contains all these operators. And this is going to be h bar divided by 2 times sigma. And this sigma right here is simply a vector that contains sigma x, sigma y, and sigma z. And what are these things? Well, sigma x is simply this matrix. So sigma x is 0, 1, 1, 0. Then we have, this is kind of awkward here, I'm going to move it. Then we have sigma y, which is going to be 0 minus I 0. And then we have sigma z, which is going to be 1, 0, 0, minus 1. Okay, so that's the way to write this. And these sigma matrices are called the Pauli matrices. And they are actually very, very, very important. They come up very often. And in fact, well, much later on, they will define the algebra for some of the most advanced quantum mechanics that I'm going to cover in this course, which will be all the way into the introduction to quantum field theory. So Pauli matrices really come up very often, and this is what they look like, this is where they come from. Something important to notice, of course, is that all of these operators are Hermitian, which is something that you expect if you want this to represent an observable, because that means their eigenvalues are real, as I proved quite a few videos ago. But something you can also see is that S plus and R minus, they are not Hermitian, which means, of course, they do not represent observables, which is something that we also know because they are just some combinations that we invented. They don't represent anything that we can measure. And these matrices have got quite a few, honestly, have many properties. I can't really discuss all of them, but some that you can see is, of course, their trace of any of these. We usually say sigma I, because, and I, well, sometimes you say it goes 1, 2, 3, and 1 represents X, 2 represents Y, and 3 represents Z. You would say 1, 2, 3. Basically, it says this is true for all of them. Their trace is 0. Okay, you can just see that right away. The trace is 0. Another important property that we have is that sigma I, any of them squared, this is going to give us the identity. Okay, this you can verify quite quickly. For example, let's go with sigma X. This is 0, 1, 1, 0 times 0, 1, 1, 0. If you do this, you get 0 times 0 plus 1 times 1. Then we have 1, 0, 0, 1. For this column, we get 0 times 1, 1 times 0, which is 0. And finally, 1 times 1, 0 plus times 0. So we get here, whoops, another 1. And you can see this is indeed the identity matrix. There are many other interesting quantities that we can calculate regarding these matrices. For example, their anti-commutator is quite interesting, which is, remember, the commutator is 1 times the other minus the other times the first one, and the anti-commutator is the same but with a plus sign. And the commutator itself can also be interesting, and there's honestly many properties that I don't intend to see in this video because, as I said, there's way too many of them, and for now they don't really mean too much because we are not going to be using it that much. But as we start to use them, I will make sure to take the time to go through them. And if there's enough interest, maybe let me know in the comments, and maybe I can dedicate an entire video just to show some more of the properties that these matrices have. So anyways, this is what I wanted to discuss in this video, because this is the most important thing that we need to know about spin. As I said, it's basically a copy of the normal angular momentum operators that we saw. And all we did was discuss it a little bit and find their matrix form. So that's what we did. And well, finding the Pauli matrices is very important because, as I mentioned, in the future they're going to be showing up more and more often. So it is good that we have already encountered them. So I will do a few more videos on spin, a little bit discussing its significance in the next video. And I think I'm going to do a few videos about examples before ending at least this part and then moving on to addition of angular momentum. So I will see you then.